Okay, we're going to do some continuations into Chapter 4, but we're also going to talk about some things from the homework. And one of the things I want to do is take a look at something with regards to this class in the midterm. I've been getting asked questions quite a bit lately about when is the midterm going to be, and I thought I'd just point you at where it's actually talked about. It's not obvious, and I need to bring it out on the top layer of the home page here, but on the lab schedule, if you remember when we went through this the first day of class, this is where it's at, if it will bring it up. So down here in this schedule, I say on week 9 is the midterm week. We talked about it one other day in class, so that puts it, if I was to go over here to the calendar and go over to March, that puts it either on the 14th or on the 16th, and we'll have some sort of a vote on that as to which day we want to have it that week. And I will have old midterms put up on the website prior to that for you to look at. There's a review sheet that we'll go through. And since we've got this document open right here, I'll just point out that another thing that's going to happen is that the labs will fade away before the end of the semester. So what I usually do is I start using Fridays for extra lecture days or questions or problem workings and things like that. You might say, what goes on at the end of the semester with regards to labs? Well, the labs that you do, once those are done, then there's going to be a team project that I'll hand out that you'll do that involves MATLAB and signal processing. And that has a little bit different flavor to it because you get to work specifically in teams, and that will be turned in. It's either turned in when you come to take, it'll probably be turned in when you come to take the final exam, since the final exam this year is on the Monday of finals week. It's the very first day, so it'll be due very close to the end of the semester, if not during finals week. Does that raise any questions or concerns for anybody? The class is looking thinner and thinner all the time, and this has happened every semester I've taught it. The videos go up over and over again, and people start not showing up after a time. You guys are here, though, so I don't need to talk to you about that. I'm not scared by it. I've seen it happen before. I mean, scared in the sense that the group on the campus that wants us to be watching out for people that are in the verge of not making it send me emails like, what can you do to keep people engaged and things like that. They want me to turn names in usually, and I've never done that. I've sometimes asked about that. There is a system, though, that I can take advantage of if I wanted to turn some names in. And I'm not saying I have any names on my mind right now. I can turn that in, and then I think you start getting emails from that network on the campus that's looking after you to see that you're not losing it. Okay, what I want to do before we continue in sampling theory and kind of revisit some of the things from last time is I want to go take a little bit closer look at this problem number 1 again. I had a question a little bit before lecture about what is x of n and what are we supposed to be doing here with this problem. So just to review for you what's going on with that, if I jump back over to Chapter 3, this is on page 3-24 in Chapter 3. When we first were introducing Fourier series, we did an analysis of a square wave. So the n-term approximation or synthesis of a signal, periodic signal x of t, is this equation 330. Oops. So it says you approximate using n terms plus the DC term, which is when k is equal to 0, your periodic signal x of t, and you're synthesizing it using the Fourier coefficients that were obtained for that signal to begin with. In other words, you did an analysis of x of t and came up with the Fourier coefficients that can be used to represent it, and now we're going to approximate it using a finite number of terms, just n terms. So the case in point for the square wave, if we dial down through that, the Fourier coefficients were summarized here in this equation 335. And then what I did as a follow-on using MATLAB is I plotted the line spectra, and then on the page after that, page 327, is where I actually synthesized the square wave. And the way I synthesized the square wave is using a function that was a rewrite of the synthesis sine function from the lab, and I had a typo in here because I didn't change part of my help file on my function, but this function is a modified version of that function that was written for the lab earlier, and I utilized that function to actually carry out the sum. So this loop in here is actually doing exactly that sum. To get the synthesis equation. So then I show an example of how to use it for the square wave right down here, where I load in n is equal to 15, and then I sweep the coefficients right in here from minus 15 to plus 15. But notice that I'm stepping 2 at a time. Why would I be stepping 2 at a time for a square wave? Pardon me? That's exactly right. I don't need to have the coefficients for A2 and A4 and so on because they don't exist. They're 0. So I'm just going to synthesize the odd harmonic coefficients. And so once I get the index k running over those odd coefficients, then I plug into the coefficients equation right here, and that gets me the Fourier coefficients from minus 15 to plus 15, taking odd steps. I'm not going to have an A0 term because I'm going to step from minus 1 to plus 1 as I stride 2 at a time from minus n to plus n. But then I loaded in manually. I forced in there the beginning of the vector k. I stuffed a 0 in there to represent the DC term, and then in the coefficients vector AK, I stuffed a 1/2 in there, and this was inserting A0, and that was inserting k is equal to 0, basically. So now I have the complete set to load into this Fourier series synthesis function, and I specify the fundamental frequency and how many harmonics I'm going to be plotting, and whatever the other parameters were, the duration, I guess, how many seconds to plot it for. So then I get the picture, and this is basically what you're going to be doing in that homework problem. You'll be creating a picture kind of like this. So all of the, I guess I'll call it the recipe, is pretty much right there on the page. In the notes, you've got the recipe for how to create the plots. You just need to customize it for these the Fourier coefficients right here. So you're going to be doing it for that set of Fourier coefficients. And notice for this particular waveform, you don't have to prove it or do the integration to get the coefficients. Notice that k is valid for all integers except 0. In that formula, you're going to calculate what A0 is up above here and load that one in manually or like I did in the sample code. And then this formula down below for A sub k is for all integers except 0. So that gives you the complete set. Why am I doing this? Well, even though we didn't dwell on the detailed calculus of having to do the integrals and work the tedium of getting the A sub k's, at least I can let you get in the driver's seat basically and take this Fourier series representation for a test drive for this particular waveform and just get a flavor for what it's like to synthesize a waveform using its Fourier coefficients. I mean, to me, when I first took and studied all this material as an undergraduate way back in time, everything was math on the page, math on the page, math on the page, and it was pretty boring at times. But now we have computer tools and we can visualize things. We can actually plug things in very conveniently and generate plots. And when I was able to finally do that, I was pretty excited about it. Actually, I taught a course on web programming once for electrical engineers. It was kind of an elective class. It was something that my department chairman wanted me to do. It taught me a bunch about web programming in general and helped me create my website, and that's kind of the reason why I have my own website and I don't use what the university framework provides through, what's it called again? College, is it Blackboard? That's what we have now, Blackboard. We've had different systems, see? I would have not liked that Rocky Road ride because I would have had to change systems about 3 times, which probably wouldn't have been a lot of fun, but at any rate, one of the first, when I taught that class, Java had just come out, and I was teaching myself the Java programming language, and one of the first applets that I wrote was a graphical one that displayed a Fourier series synthesis of a square wave. And then I had the students in that class program an applet to do the graphics for that. So that, you know, that excitement continues in the sense that seeing is believing as opposed to just math on the page all the time. And I'm making it sound kind of crude when I say math on the page, but you know what I mean, since most of you are still taking calculus. Does it sometimes get kind of dry and obscure? Engineers don't lead a life like that. Trust me. As a matter of fact, once you get into real engineering, you're going to say, when was the last time I used calculus? Not that you won't ever use it, but you don't use it all that often. A lot of people tend to forget a lot of the things they learn. It just depends on what type of job you're in. Instead, you end up doing a lot of other things that some days you'll say, I wish I could do some real engineering again, because it's not always that way. I mean, you have other issues to go deal with. Sometimes it's dealing with people, right? Or I had a guest speaker in my senior seminar class last week who, at the end of his talk on a case study, gave some philosophies on engineering, and he gave 2 things that I've heard over and over again through my career. What makes for a successful career, and what are things that really allow you to go far? The ability to communicate, and we were talking about tech writing. It's exactly what that tech writing class is supposed to be about, teaching you how to write and communicate with fellow engineers and managers, being able to express your ideas in writing and in presentations to customers and so on. Those are the things that really make the difference in the end. It doesn't sound very exciting right now to say that, though, does it? You'd rather, I know, be designing something, because that's what I like to do, is design stuff, test it in the lab, or write code, whatever. But that communication skills stuff, not the EE communication stuff. My area is communications. When I first started teaching here, I got interviewed by the scribe. This was decades ago. And they asked me what I did, and I said I teach communications and signal processing, and I had to explain what type of communications I was talking about, because I did not want to have it be confused with the communications department in letters, arts, and sciences. You guys know the difference, right? There's a huge difference. No one ever harassed me about that from the communications department down there. But does anybody have any questions and any of the other homework problems? We're going to get to the number 4 type of problem in the lecture today, and I'll explain that.
Just got a real quick question.
Okay.
As far as the test goes, my understanding said that we're going to see the DC component possibly in the test, but we're not going to see Fourier coefficients.
Where you have to calculate things? No.
Because I'm still kind of, like I said, I can do it with a function.
Mm-hmm.
On MATLAB. Like I said, if I had to do it on paper.
But one exception to that would be the way that quiz ran from last Friday. I mean, that was a very simple one, but you had a homework problem on the set before where I gave you several cosines, then you had to discern the Fourier coefficients. And remember, what's special about Fourier coefficients is they're unique. No matter how you arrive at them, you've got them once you've got them. And so the Fourier integral, that analysis expression, is the official, get it for good solution technique, but it sometimes is very tedious and messy. If you can back into it, like with the Euler's identity and expanding and then recognizing A1 and A15 and A minus 15 and all that from Euler's inverse identity, that is just as good, and that's something that I do want you to be familiar with. That doesn't involve any integration, right? It's just manipulation. And spectral ideas, harmonics. A Fourier series, remember, only works for periodic waveforms, so the spectrum is always going to have spectral lines in it that are harmonically related. Whereas the line spectrum, when it was first introduced at the start of Chapter 3, there was no notion that the spectral lines had to be harmonically related. That wasn't a requirement. But in a Fourier series context, everything has to have a root frequency or fundamental frequency that it's based upon. That's a good question, because I know that there's anxiety about Fourier series amongst some of you, and probably some people that aren't here today are anxious about it, but they're not even here, maybe because they're wanting to hide from it. I don't know. Sometimes unless you confront your fears, you can't get over them, right? So, any other questions? You will see Fourier series again, though, so it's not the end of it. Okay, sampling theory. I think we made good progress on the topics and understanding concepts of sampling theory last time. We had spent quite a bit of time on this example where we had the 60 hertz, 340, and 460 hertz sinusoids, and we sampled at 400 hertz. So I put out pictures in MATLAB. And remember this particular setup, the way I modeled it and everything, the phases all match up. So for all three scenarios here, whether it's the 60, the 340, or the 460, they all alias to the same fundamental alias, which is 60 hertz relative to 400 hertz sampling, and the samples are all identical. And when you look at this plot, you're convinced of that, right? Whether you got it by sampling the 60 hertz or the 340 or the 460, the sample values you get look identical. And if you tried to reconstruct and get back what you started with, you'd only be successful with the first one, right? Because if you tried to reconstruct the second two waveforms, the 340 or the 460, using those green samples, sampling theory would say that we're not going to get 340 or 460 back. We're only going to get back the principal alias frequency-based signal, and that would be the 60 hertz signal. We're going to talk about reconstruction here a little bit later, but just by looking at the way the green dots are stacked up, you'd say it looks like a sinusoid, but it doesn't look like a 340 or a 460. It looks like it's the 60, right? Just graphically, how it fits together. We also talked about how looking at things in the analog frequency axis, in a lot of cases, I think is more practical because you can get things in terms of the physical world, thinking of the sampling rate and how aliases occur relative to multiples of the sampling rate. And then you can convert to the digital frequency omega hat by just, you can always go to omega hat. It's not written right handy here, but omega hat is just 2 pi times f over Fs. So in this case, when you do that conversion on those three frequencies, you get 0.3 pi, 1.7 pi, and 2.3 pi. And the principal alias is right here, and why is that the principal alias in the digital frequency axis? Remember last time we spent a lot of time on the principal alias band in the analog frequency axis, and that was 0 to Fs over 2, remember? So what's the equivalent band on the digital frequency axis for being a principal alias from last time?
Between 0 and pi?
Yep, exactly. Because all you'd have to do is plug in place of F here, plug in Fs over 2, and that's the maximum frequency we can go up to. We can approach that value and not have aliasing, and we plug that in, we get the Fs canceling, and we get 2 pi over 2, which is then pi. So that's the highest frequency we can go up to before aliasing commences. And so looking at over here at this 2.3 pi, we can see in the digital frequency axis that it is an alias, because remember, aliases would be like 0.3 pi plus or minus k times 2 pi because of the 2 pi mod 2 pi property of the cosine or the sine function. So sure enough, 2.3 pi is 0.3 pi with 2 pi added to it. So what about 1.7 pi? How does that factor in as an alias from this model? It's got to be related to 0.3 pi somehow or another, but how did that work out from last time? It might help if I put absolute value signs around that. It'd be when k is equal to -1, right? That's how that would come out of there. It's a little bit more abstract to see it in this sense. I mean, I don't have my pictures from last time, but I can draw up another set of pictures if I want to. This is the frequency axis in hertz. Then I'll put omega hat down below that. Suppose this is our first input frequency. That's F1. Then signal frequencies that alias to F1 would be a spectral line that would sit at Fs minus F1, or this one is at Fs plus F1, right? And then what's the next set of aliases above that? Well, they're F1 either side of 2Fs is where they would lie. So there'd be a pair here and here. So this would be 2Fs minus F1, 2Fs plus F1. The key is that there's a difference in here and in here that makes those frequencies, the delta between Fs minus 1, F1, and Fs is F1. So that's what makes it an alias. And then experiment with different colors, I guess, since I've got them. So all of these have differences relative to multiples of Fs that are F1, so that means they all alias down to F1. I probably did it differently last time because we were looking at it in the opposite direction, going the other way, but this is just another way of thinking of it. aliases are going to lie F1 above and below FS, 2FS, 3FS, and so on and so forth. That's another way of just visualizing where the aliases are. And of course, the principal alias has to be something that lies on the interval 0 to Fs over 2. And if we go through the conversion formula being that omega hat is 2 pi times F over Fs. So that's how we go from the frequency axis in hertz to the omega hat axis. Then Fs over 2 corresponds to pi, Fs corresponds to 2 pi, and 2Fs corresponds to 4 pi. So when I was asking the question earlier about what is the principal alias on the omega hat axis, we spend a bunch of time on it being 0 to Fs over 2 in the analog frequency axis in hertz. Then it's just getting fixed in your mind that there's this parallel axis that runs below the frequency axis called omega hat, which is just a remapping of the axis through the equation down there. So pi corresponds to Fs over 2, 2 pi to Fs, and so on. This is actually the key to understanding the last homework problem, too. I'll come back. Well, maybe I can talk about it a little bit right now and see what your reaction is to it. If I sample a signal and it's less than Fs over 2, it's properly represented as its original frequency because there was no aliasing done to it. So if it comes into the system, my signal processing system through the A to D converter as F1, it will just come right down here and show up as omega hat 1. Agreed? Through this equation right here. Now suppose I decide just draw a block diagram here to say that x of t is up here, and we're looking at the spectrum of that. And then we take and run the A to D on that, and we're sampling it at Fs. We get a sequence, x of n. And that sequence will have a line spectra on the omega hat axis. So the frequency that comes in at F1 will be at omega hat 1 on the omega hat frequency axis. And then if we were to go to the next level and convert it back to the analog domain using a digital to analog converter, so we'd go back to, let's just call it y of t. Then we could go over and again do a spectral plot. Frequency axis in hertz. So assuming that we have this box that can convert the samples back out into a continuous time signal, and that's something we haven't really explained yet, but we're getting there. Intuitively, though, where should those sample values and the frequency axis at omega 1, where should the spectral line show up at the output of the D to A converter if things are consistent? It gets sampled at Fs. It was originally analog frequency F1. It becomes omega hat 1. So intuitively, shouldn't it come right back out here and sit back where it started at? So it should be back at F1 again. And that's what the math talks about a little bit later in the notes and in the book. What aliasing does for us, though, with this model is if the signal came in over here at one of the alias frequencies, Fs minus F1, because of the aliasing and because of the fact the D to A converter and the principal alias band are kind of synonymous, you cannot reconstruct anything outside the principal alias band with the digital to analog conversion process. So Fs minus F1 aliases to F1, and it will then get converted to omega hat 1 in the sampling process, and it will be output as F1 as well. So it lost its true identity in going through the sampling and then the reconstruction process. And isn't that exactly what happened when you did that chirp signal at the beginning of the lab last week? You tried to represent a chirp at 13,000 hertz, or a sinusoid at 13,000 hertz, and you were sampling at 8,000 samples a second, right? I think that was the number. So you go up to 2 times Fs was 16,000 hertz. That lies 3,000 hertz above 13,000. So that means the difference frequency, or the principal alias, is down there at 3,000 hertz, and that's what you heard, right? You heard a much lower frequency. That's the theme of the last homework problem. In the end, it just says follow the rules. Bring an input into the A to D converter that fits within the band 0 to Fs over 2, and it will come back out the D to A converter at the same exact frequency it went in at. So that's playing by the rules. If you bring a sinusoid in that's greater than Fs over 2, then it's going to alias down to something in the principal alias band, and it's going to come out, at that alias frequency, which is not playing by the rules. You're basically accepting the consequences. In certain applications of sampling theory, that's workable. In most applications, it's not. In certain communication signal processing scenarios, that's actually a desirable feature, and I'm not going to try to explain that right now because I don't want you to get confused to think that aliasing is necessarily a good thing. For speech signals, it would not be a good thing at all, because it would mean that our speech would be all, garbled up sounding. Spectral content would be shifted to different locations, and I guess thinking of a science fiction movie, you'd sound like an alien talking or something if your spectrum was all shifted or inverted around. Hopefully I'll give you a demo of that. I've been waiting for a donation from National Instruments of a nice little tool that I promised them I would try to use in this class. I wrote a proposal up, and they still haven't shipped it to me yet, but it was going to allow me to do some nice little easy demos in class. Have any of you ever heard of LabVIEW as a software tool? Okay. That's what National Instruments makes. You may see, if it works out well, it may actually be part of the curriculum starting next year, possibly. I don't know yet, though. The evaluation of it is not happening. 2 of us were going to evaluate this product to see if we would start using it in circuits and electronics starting next year. Okay, this example right here, I think, I'm not going to go through the intimate details of it, but let's just take a look at this little plot right here, and this will help explain this other point of view with the pi axis, or the omega hat axis. So this is a way of just looking at the analysis based on the omega hat axis rather than the frequency axis in hertz. So with 0 to pi being the principal alias band, we can see that if we have a signal at 0.7 pi, one of the alias frequencies is at some multiple of 2 pi on top of that. What frequencies are aliases to 0.7 pi? Or maybe the first thing is 7.3 pi one of its aliases? Yes or no, and why? Okay, you say yes. Why?
Found the difference between 7 pi and pi is 0.3 still.
It should be 6.3 pi and 8.2 pi.
Well, let's just think back. 2 pi 4 pi, 6 pi, and 8 pi correspond to fs, 2fs, 3fs, and 4fs, right? So the differences have to be with respect to those values, the even multiples of pi. I think that's what you're trying to say, but you didn't quite say it like that.
Other side, or on the.
Well, is it okay, though, if it's sitting right there and look at how it lies relative to 8 pi? What's that difference sitting in there?
0.7.
So that's it, right? So that makes it work. So in each one of those intervals, whether it's a blue interval or a red interval, and I kind of made them like even and odd intervals, there should be an alias frequency. So pick one. I mean, we can find another alias in here by just picking one of those little colored bars and finding out where the frequency should be. So let's pick this interval right in here. Where's the alias that corresponds to 0.7 pi on that interval? 5.3 pi, you said? Okay, does everybody agree? Okay. What about this interval right down in here, the one that's really close to home or close to the principal?
1.3.
Okay, 1.3 pi. And then if you wanted to pick one on the other side, how about that interval right there? Okay, so that's at 4.7. Is everybody getting this?
So we're going
See, it's easy, right?
We're going from 0 to 0.7 pi is how we're finding it, right? Instead of going, because we can't go from 2 pi down, it has to be between 0 and pi, right? That's right.
0 and pi is the principal alias band, so that's right in here. That's the real frequencies. If we reconstruct from if we reconstruct a signal, that's where the frequency is going to come from. It's from that interval right there. And of course, I can always draw another axis down here. I can always draw f, and then I can say corresponding to 2 pi is what? That's fs. So 4 pi is 2fs. Really, with sampling theory, when you get down to it, I call this the back of the envelope kind of calculation, where you're just scratching something out. And if you're trying to get your mindset, to me, drawing a picture out and then drawing the corresponding axes is just really helpful in trying to get your mindset on what's going on. If you're a visual thinking type person, the equations can come later, but I don't want to leave anybody behind. Is there anybody in here that is missing out because the math is the only thing that works for you right now? I know we have a guy who's more of a mathematician kind of guy in this class, but he didn't come today. So he might say something different to me, but so if you like to see it in hertz first, then you would start doing your working here, and then you could switch over, convert over, or vice versa. What this example did is it looked at the phasing business. The frequencies will be identical, but it's possible to have the phasing off so the samples aren't exactly in the exact same locations. And this is an example where the 0.7 pi signal trying to be the principal alias to the 7.3 pi signal, when the plus signs were used, didn't lead to the right set of samples. But as soon as I change the sign of the angle, then the samples line right up. The phasing is not as important as just the frequency is, though. We don't always have to have the samples be identical. It's still going to be a sinusoid at that same frequency. It's just the phasing might be different. The phase of the samples could be different. So all the aliases are those signals that lie either side of multiples of the sampling rate relative to the principal alias frequency. We've already been talking about this spectra extensively, and in the next lab, the one you do after lab 5, you'll be working with a GUI that makes pictures kind of like this example right here. This is just another way of looking at it, though, yet another way, where if you look at it on the omega hat axis, because we know a sinusoid always has a positive and negative frequency spectra, we could actually extend the notion of the principal alias band to run from minus pi to plus pi if we wanted to. It doesn't destroy anything mathematically, because we know for a sinusoid that has a frequency omega naught, if we plot its spectra, we actually have a spectral line at the positive and negative frequency location, right? It always has to be that way for a real sinusoid. So in reality, those two red spectral lines are the principal alias spectral lines for a sinusoid at omega naught hat. And then if we take and add 2 pi to those two red lines, this one shifts up to here and this one shifts up to here. That's one set of aliases. And then another set of alias frequencies are when we shift the whole thing down by 2 pi. And that's another set of aliases. And then you can do it again and again and just expand out all the aliases that show up on the frequency axis. Does that seem too confusing? If you're good with that, I'm going to show you something else and see if this is acceptable. This is kind of an advanced topic, but since I have it, a little tool that I wrote called Sampling Theory. This takes and looks at the spectrum normalized to a frequency of 1, so I normalize by the bandwidth of the signal, or the highest frequency of the signal. And this supposes that instead of being spectral lines, the spectrum of the signal is made up of a continuum of spectral information, and that's more like it really is in modeling. So we have a high value at DC, and then it goes down and finally disappears when we hit unity. So the sampling theorem that we're about to officially write out on paper says that we have to sample at greater than twice the highest frequency. And the reason for that is because when we looked at what we were just looking at, we had the principal aliases, the two lines here and here, and then we translated it up by 2 pi or translated it down by 2 pi. In order to keep those spectral translates from colliding with each other, which is what aliasing is, we have to sample at greater than twice the highest frequency. So this is kind of a graphical thing, but I'm going to dial it all the way up here to the sampling rate over the bandwidth of the signal is now double, which means we're satisfying the sampling theorem. So the translates are the ones in red. That's the images that we get when we shift up by 2 pi or down by 2 pi. And another way of looking at this, and not a requirement in this sense for this class, this is just a more advanced way of looking at it, which I'm trying out on you to see how well you can accept it. It's just an experiment. You can see the red ones aren't overlapping with the blue at all. And the blue is like the original signal before it was sampled. But then when we sample it, we have availed ourselves to the potential of aliases that could come in up here or could come in down here. So if we sample at a high enough frequency, none of the reds overlap with the blues. But if I sample too fast, then I can even move those translates further away, so I'm in less danger of having an aliasing problem. But if I don't sample fast enough, then here's what happens. You start getting this overlap, and that's another way of depicting aliasing. If I was not sampling at a high enough rate, what would happen is if I tried to reconstruct this signal, we would get back portions of the blue, but where the blue overlaps right in here, it folds around, and now I'd hear, instead of the spectrum that would go up higher in frequency, suppose that was part of my speech, it would instead get mirrored about that crossover point, and I'd hear all those frequencies actually out of the lower aliased frequency. And that is going to sound like what? Exactly. It sounds bad. Is that believable? there comes a point where something tries to cross through Fs over 2 and effectively is folding over, hence the term folding frequency, and that's what we hear instead of what was actually gone above that, because the aliasing just makes that happen. And if I sample at a really low rate, this is what happens. Translate upon translate is just all folding multiple times like an accordion on top of the usable band. And if the first translate folding sounded like crap, what does it sound like when you have 5 of them folding on top of each other? It's, multiplied by 5, I guess. It's like all on top of each other. It doesn't have to just be the signal content. Suppose you had a really wideband sampler, a really wideband front end of your system, and you didn't protect it, and there was a bunch of noise out there. The noise will alias down and stack up into the band of interest too, so noise will just pile up and it will sound just plain noisy due to ignorance about aliasing. It's intriguing, I guess, is what I'd say. Radio signals, though, and I've got a kind of another example in here with bandpass signals that look like that just occupy a narrow band. Nominally, you'd want to sample those at greater than twice the highest frequency like here. But notice, because of the gap that's in here, what happens if I don't sample according to the Nyquist twice the highest frequency rate? There I'm getting a total collision, but as I bring the sampling rate down, what's happening? I now have a clear zone again. The only thing is I have to understand that the red ones are the aliases and the blues are the originals, but in some radio applications, I might undersample by a whole lot, and I understand how to process this signal in red that's close to the DC point, and I can utilize some cost savings in terms of processing power. I can basically downsample the signal and use a processing engine that can operate at a lower clock rate or use less resources in terms of CPU power. So there's tricky things you can do with sampling theory. This sort of stuff gets talked about in the modern DSP class that I teach in the fall, which is an elective that you guys could take as a senior, or you could come back as a graduate student and take. So sampling theory has a lot of extra nuances that go on with it. We've basically seen the main points already in this class, except for a little bit of reconstruction. Any questions on this? This is kind of exotic looking, but hopefully you're thinking, everything's got deeper and deeper you go to get, innovations and ways of doing things that can make your product more cost effective or more feature rich. Okay, the folded strip we went through already. This is just the folded strip idea in terms of omega hat. The one that I handed out in lab last Friday was frequency in hertz, remember? It's just rescaling of the axis. It's the exact same idea, though. Okay, here's the statement of the sampling theorem. And this will be important in working homework, quiz problems, and so on. We must sample at a rate Fs at least twice the highest frequency. Or in mathematical terms, we choose Fs, which is 1 over the sample spacing, greater than 2 times B, where B is the bandwidth or upper frequency extent of the signal we're sampling. So for our speech, for example, we contend, in telephony at least, that our speech bandwidth only goes up to about 4 kilohertz. So in speech telephony, like wired telephones, cellular telephones, the sampling rate is 8,000 samples per second. That's what's utilized to digitize your speech. And just knowing that by me telling you sample at 8,000 samples per second, your brain should immediately say, oh, so I can only get a usable spectrum up to fill in the blank, 4,000. Does that follow then? Because it's the Fs over 2 value. So why does speech on a telephone sound not all that high fidelity? Because 4,000 hertz is not all that high frequency. Our hearing is definitely much better than that. Okay, this example here is basically springing off of that, but this is the example that is very similar to what you did in the lab last week. This is a picture out of the book, actually. Sampling rate 2,000 hertz. So the usable frequency range goes up to what? If it's 2,000 hertz sampling rate, what's the usable frequency range? 1,000. So this just shows you a chirp, for example, a chirp that's sweeping linearly from 0 hertz up to 2,500 hertz is the way this example was set up. As the signal linearly chirps up at the input axis here, as it hits 1,000, the folding frequency, pick a different color. The folding frequency, or fs over 2, is 1,000, so even though the input frequency keeps going up, it folds because the principal alias lies beneath that, so it heads on down until you reach 0, but 0 is where you're hitting, the actual input is hitting 2,000. So now with what we've been going through, when you hit 2,000, you know why the output goes to 0, because the difference between the input and 2,000 is now gone to 0, right? And then as it passes through 2,000, the difference grows up again and it heads up in that direction. Hopefully by now what you were doing in the first part of the lab last week is just more and more clear in your mind as to why it chirped, you know, and that zigzag pattern was based on all the sampling theory principles. I wrote a little helper function that can actually plot the output frequency from the input frequency, and I think it's in the homework where you can test this function out if I'm not mistaken. Well, it looks like I didn't give a problem where you get to test out that idea. You can play around with it and use it in your lab, though, if you want to. You could use this to put in a range of input frequencies, either as a vector or as a scalar, and then this function searches for the principal alias. And it does it algorithmically. It basically uses the idea we were using by looking on the sheet of paper with the frequency axis. It's looking for a difference between the input frequency and some multiple of the sampling rate that is less than fs over 2. So it's set up using a while loop. It says while f out of n is greater than fs over 2, keep looping. And what it's doing inside the loop there is it's letting f out be f out minus fs. So when it first subtracts fs from f out, it gets it to within, you know, a delta of fs, and if that absolute value is not less than fs over 2, then the next loop it subtracts fs again and sees if it's within a you know, fs over 2 delta of that next multiple fs, and it keeps doing that until it gets a hit, and then it stops. Does that look too crude? I mean, it's brute force, right? It's just saying I don't know where it's going to be, and I have to test which multiple of fs is that frequency within fs over 2 of. So it just does it by trial and error. So here I just, you know, exercised it just to verify that it can create a picture just like that one that was in the book. Okay, compact disc digital audio is 44.1 kilohertz. So that means we can represent analog input signals up to 22.05 kilohertz. The next topic, and kind of the the tail end of things in the chapter is how do we reconstruct. So the reconstruction idea is the digital to analog converter, or what the book calls the discrete to continuous converter. That's the mathematical terminology for the digital to analog converter. So it's a box that has an arrow going in from the bottom that tells you what the sampling rate is. And what this box does is it takes the samples, y of n, and places them back on the time axis for playing back as an analog waveform. Now what the D to C also has to do, once those samples get placed on the axis, you have to perform interpolation to make it look like a continuous waveform. So it might start off by just having a short, ideally zero width pulse, but actually in actuality a finite width pulse being placed on the time axis at an amplitude that corresponds to the individual sample values. But in actuality, what a D to A converter really does is it uses what's called a zero order hold interpolation. So this is the more common situation. You put a sample value on the axis at, say, t is equal to 0. You hold it for one sample clock period, and then you get an update. You read the next sequence value, and then you stair step to that new value. And then you continue to do this sample and hold operation. In that fashion. So you're creating a stair-step approximation to the sample values. That's called the zero-order hold. That's the way most successive approximation converters would work. But again, if you go with the sigma delta technology, remember we talked about the technologies last time, the same technologies that are available for A to Ds are basically run in reverse for D to As. You can get smoother interpolation. Another type of interpolation is linear interpolation. But this is not generally implemented in a converter. It's just not practical. It's generally, if anything, it's the zero-order hold, and then you have to follow that up with some more filtering. Or if it's the delta sigma converter, some of the smoothing and reconstruction is built into the signal processing inside the converter itself. Formally, what we need to do is we need to have some sort of pulse function in here that will take the sample values and interpolate between them in order to get the reconstruction to take place. So when I was drawing up a picture early on the scratch sheet, this picture right here where we went input x of t to x of n, after we go through the A to D or continuous to discrete, and then back out to the analog world again through the D to A, it was this picture right here. So this is a basic DSP signal processing system for analog signals. So it's composed of a box in the middle which has algorithms in it that run on sequences, and then it has an analog interface or analog input circuit, the A to D converter, that's clocked at fs samples per second. And then in order to get the samples from the digital signal processing system back out to the analog world requires the discrete to continuous or digital to analog converter. So since we live in the analog world, we would say, and a digital signal processing person would say, I will take your analog signal and I will process it on my computer, my dedicated DSP computer, and I will return it to you as an analog signal. And all I need to do is have these three basic blocks: the mixed signal analog to digital, the DSP algorithm processor, which could be a dedicated microprocessor, algorithms running on a FPGA, an ASIC, an embedded system of some sort, and then I need another mixed signal part called the digital to analog converter. We're going to be spending the rest of the semester after this chapter focusing on that box right in the middle. we're going to keep coming back to the converters that go on either side and how to interpret what goes on, but that's kind of going to be our focus from here on out, starting with the next chapter. So, any comments on this? Is this green technology? I'm just smiling because that's in the news a lot. Suppose all we wanted to do was amplify the signal x of t to produce y of t. Which system is better? Do we need all that hardware up above if all we want to do is gain scale the signal by a constant? In other words, basically raise the volume by a certain amount? We probably wouldn't instantiate all that hardware on a PCB if all we want to do is put some gain on it. But if we want to do some very precise filtering, maybe to remove some annoying hum or remove some strange artifacts that are in the signal that we really can't tolerate, then we might need the power of the DSP algorithm. So then we'd bring it into the discrete time domain with the A to D or C to D, process it, and then send it back out again. Or another scenario would be maybe we don't want it back in the analog form. Maybe we just want to take it in and do processing and put it up on some display or run some algorithms against it that with the data samples to say, is there a target present? You know, is there an aircraft approaching at some closing velocity that we need to be tracking? Or the opposite scenario is we have a bunch of information we want to play back that we've previously recorded, like in a music player, and it's stored conveniently in digital form, so we play it back out through the D to A converter. So there are different scenarios, but I think as engineers we have to be responsible too, and that's part of the professionalism that you do in the capstone sequence, you know, designing things that are sustainable and that just plain makes sense. Just because we love this technology doesn't mean we have to make everybody use it in a needless, unessential way, like put a digital signal processor in a garbage can or something. I'm just thinking exotically, what would you do with that in a garbage can? Have some sort of a detection system, so if the wind tries to blow it off your driveway, it rights itself and rolls back up. I mean, right, we could dream dreams on different things. If you're a homeowner, you know how annoying it is to come home and find your garbage can blowing down the street. Maybe it's been run over and it's in shreds. I've had that happen before too. I didn't preconceive that. That was just something that just hit my brain now. I mean, you guys will be dreaming up ideas of things to make, and you got to be reasonable. Okay, what else do I have in here? This is something that doesn't get played out a whole lot in the class, but it's very important. If we're going to build a DSP system like we've been talking about, one of the things we have to make sure is in the continuous to discrete block, it's up to us to ensure that we don't allow signals in above Fs over 2. And that amounts to building what's called the anti-aliasing filter. Because in most applications, we don't want to have that sound we were talking about that sounds bad, but from aliasing. So it's up to us to put an analog filter out in front or use an A to D converter that has it integrated, which the sigma deltas do. And we just set it to make sure signals above Fs over 2 get sufficiently attenuated that they don't cause us any harm. Because we accept the fact that when we use the A to D and D to A, or the sampling theorem concepts, we know that we can't properly represent any signals that come in at Fs over 2. So it's having respect for what the math tells us is possible and not possible. And then, of course, the D to C is designed to reconstruct in that band from 0 to Fs over 2, or if we think of the entire positive to negative frequency band minus fs over t to plus fs over t. So this leads to this discussion, which is related to the last homework problem, which is an end-to-end system where we visualize having a C to D, DSP processing block, and a D to C. At the present time, we're going to assume that the DSP processing block is nothing more than a hard connection of the input to that block to the output, because we haven't gotten into the discussions of those blocks yet. So if I was to go back up to here, this direct connection means that we just have a wire going right through there in our block diagram. So we just xn becomes yn until we define an algorithm that sits in the middle, which is, like I said, topic of the next chapter. So we bring in a signal at 500 hertz. We're sampling at 2000 hertz. What can happen at the output, or what can happen once we sample, is we have to take ourselves down to the omega hat axes. Remember how we do that. We translate everything through the equation. Omega hat is 2 pi f over fs. So 500 becomes 0.5 pi, and so on. Have we satisfied the Nyquist sampling theorem in this setup? 500 is less than fs over 2, so we're good. We do have aliases that could exist at those dashed line locations, but our input didn't come in at any of those frequencies, so we input at 500, we sample at 2000. When we get ready to go the last step, namely to output it back out, then we're going to use the equation. We're going to invert the equation above, and we're going to have f is equal to omega hat times fs over 2 pi takes us back out again. And assuming the omega hat is the principal alias frequency, then the output frequency will reconstruct back out at 500 hertz, right where it came in. So we're perfectly good to go, and the red dashed box going around in here is just to signify that the reconstruction only allows us to reconstruct in this band right in here. On the other hand, if we bring in a signal at 1500, drawing it out on the same sort of a setup, 1500 is in violation of the sampling theorem, right? So it's going to alias down to this 1500, actually aliases down to 500. So the alias shows up right in here at 0.5 pi. The real signal is sitting right up in here, but when we try to reconstruct, we don't have access to that real signal because it's been aliased to the principal alias frequency of 0.5 pi. So when we go to reconstruct, we reconstruct it back out at 500. Of course, there's other examples, and that's the kind of things. I mean, I didn't get a chance to walk through this. However, this is the type of stuff on the quiz. Let's spend maybe about a minute, because that's what my clock says we have left. So we're sampling at 2500 hertz. Is there any aliasing present? There is, because right away you see, well, I pulled a little trick in here. You got to be careful. That's the frequency of the first signal, right? 1000. Here I didn't factor the 2 pi out. So what's the frequency of that second signal? 3000. It's 3000. Watch out for that trick. I mean, just representation thing. So 3000 is not less than half of 2500. So my approach, sticking with the pictures idea, would be to say I'm going to put in 2500. I know I've got 250. So 3000 is sitting right up in here. Next alias band up is 2 times 2500, which would be 5000, right? So what's the delta in here? It's 500. So that means that guy alias is way down over here at 500. Then I've got a real signal at 1,000 sitting in there too. So aliasing is present, and the way you just write that down is you'd say yes, because 3,000 is not less than 2,500 over 2. What are the principal alias frequencies? We just sketched that out. 500 and 1,000, right? Those are the two frequencies present in the principal alias band. Finding omega naught hat, that's just working the equation I've been writing up multiple times, 2 pi times f over fs, but you have to load into here the principal alias frequency if you want to get omega hat in the principal alias band. Then the spectral plot, I kind of already have done that. No hard calculus, just simple math, but you got to know what you're doing, and think multiples of fs. Don't think pi or 3 pi or 5 pi. You got to think multiples of fs or multiples of 2 pi. That's the differences between frequencies, and those multiples is how you get down to your principal alias frequency.
Is that what the quiz on Friday will be over, probably?
Yeah,
Okay.
this kind of stuff. Some subset of this is my intention. We're just about to the end of the chapter, so we'll be starting finite impulse response filters next week.